By the end of this module, you will have a basic understanding on constant air volume application. How a constant air volume system works, traditionally, and Danfoss retrofit solution. The key benefits of using a VLT HVAC drive in constant air volume system conversion. In this module, I shall introduce you to a constant air volume system. Commercial buildings use central air handling units to distribute air throughout the building. The first and simplest method adopted for maintaining comfort was using constant air volume systems. Let me describe constant air volume systems to you. In these systems, a constant volume of air is delivered to meet the ventilation requirements within the building. To provide a comfortable environment within the building, the air is heated or cooled as required by the digital controller, modulating a coil control valve. When constant air volume systems are installed, problems like poor air distribution, inadequate ventilation, or overheating are less likely to occur. Thus, we find that this is a simple system that provides comfort. But this comfort is provided at a high cost for energy. Today, the consumption of fan motor energy, combined with the cost of heating or cooling of excess air, has caused constant air volume systems to become less desirable, and variable air volume systems to be preferred. Conversion of a CAV system to a variable air volume system is easy to accomplish with a VLT HVAC drive. We shall look at a traditional constant air volume solution. First, let me list the various components in it. A typical constant air volume system consists of the following parts: heating and cooling coils, dampers, sensors, digital controller, fan. A room, or return air sensor, is used as an input to the digital controller. The controller heats or cools the discharge air by modulating the dampers and valves on the heating and cooling coils to meet the needs of the building occupied zones. Outside air is drawn in by the air handling unit fan and is mixed with the return air by modulating the outside and return air dampers. The exhaust damper is modulated in parallel with the outside air damper to prevent building overpressurization. When the room temperature is below set point, the outside air damper is at a minimum position required for ventilation codes. As the room temperature increases, the controller commands the heating valve closed and modulates the outside air damper open to maintain set point temperature. After the outside air damper is 100% open, next the controller commands the cooling valve to open, in sequence with the damper. When outside air is too warm to be used for ventilation, the controller commands the outside damper back to the minimum ventilation position. The graph shows the outside damper position. The supply air is then distributed through the ductwork to each zone within the building. Individual room terminal units are sometimes used for final tempering of the air. It is to be noted that the fan is either on or off, depending on the requirement. The fan is on, with a maximum flow, or off. Take a look at the illustration. You can notice from the graph that, when the fan is off, the flow is zero, and hence there is no pressure. Similarly, you can see that, when the fan is on, the flow is maximum, and hence, the pressure is high. Thus, we can see that in the traditional solution, when the fan is on, the energy consumption is maximum. We just saw the working of a traditional, constant air volume system, and found that it is a simple method of maintaining comfort, but it has the disadvantage of wasting energy. Now, let us see the Danfoss solution applied to constant air volume systems. Existing buildings, and some new buildings, have constant air volume systems, despite the fact that the load varies. Loads in buildings are due to internal and external sources of heat. Internal sources are lights, electric equipment, and people. External sources are outside temperature and solar radiation. As the load varies over time, an opportunity exists for significant fan energy savings by converting a constant air volume system to a variable air volume system. A variable air volume system varies the airflow based on the actual building loads. Existing air handling units and distribution systems can be converted from constant air volume to variable air volume, with some modifications to the fan and air distribution system. To convert a constant air volume system to variable air volume, fan capacity control is required. This can be done by using discharge dampers, inlet guide vanes, VLT HVAC drive. Discharge dampers produce little energy savings. Inlet guide vanes provide some energy savings, but are costly to install on existing fans. VLT HVAC drive provide the maximum fan motor energy savings, and are easy to install than discharge dampers or inlet guide vane. Converting a constant air volume system to a variable air volume system can result in fan motor savings of almost 50% in typical applications. Controlling room temperature, air quality, or both, a constant air volume system can be converted to respond to varying building load conditions and make significant energy savings. Instead of varying the temperature of the supply air, as done in traditional CAV control, the VLT HVAC drive changes the volume of supply air as the building loads change, while the supply air temperature is kept constant. The volume of air can be varied based on room temperature, occupancy, or other air quality. You will see that installation of a VLT HVAC drive and the addition of a supply air temperature sensor converts the CAV to a VAV system. An additional supply air temperature sensor is installed in the ductwork and connected to the existing digital controller to control the heating and cooling coil valves. The supply air is maintained at a constant temperature, just as with variable air volume control. Fan motor speed is controlled using the existing room temperature sensor wired to the PID controller in the VLT HVAC drive. If a CO2 sensor is used as a measurement of the occupancy, the feedback from the sensor to the VLT HVAC drive controls the airflow and maintains the proper CO2 level. The programmable minimum speed of the VLT HVAC drive is used to ensure that the ventilation air change requirements of the building are met. Above the minimum speed, the airflow is varied based on temperature, carbon dioxide, or other variables, which fluctuate depending on the occupancy level. Let us consider the constant air volume system having a return fan. The return fan draws air from the individual zones and returns it back to the air handling units, where it is recirculated or exhausted. A constant air volume system with a return fan uses volume matching control to maintain proper building pressure. Volume matching employs duct-mounted airflow stations for measurement of the supply and return air volumes. Each airflow signal is connected to the two-input PID controller in the return air VLT/HVAC drive. The return fan speed is modulated to maintain a set difference in the amount of air supplied to and from the occupied zone. I hope you have understood the Danfoss solution for improving the performance of constant air volume systems. This solution offers a lot of energy savings. Let's see how the energy savings are obtained. As the building load decreases, the room temperature decreases. The temperature sensor transmits this lower temperature to the VLT/HVAC drive to slow the fan motor speed and provides less air volume to maintain the set point temperature. Changing the motor speed reduces fan volume and fan static pressure. A new series of fan curves are generated. The fan operates at reduced volume along the system curve from point A toward C. Reducing fan volume and fan static pressure brings the zone temperature back to the set point. The VLT/HVAC drive runs the fan motor at variable speed, which results in maximum power kilowatt savings. Let us review the key benefits of converting the constant air volume system into a variable air volume system. Conversion of a CAV system to a VAV system is easy to achieve with a VLT/HVAC drive. VLT/HVAC drive provide the maximum fan motor energy savings and are easy to install. Converting a constant air volume system to a variable air volume system can result in fan motor savings of almost 50%. An advanced feature of the VLT/HVAC drive is its ability to accept two input and set point signals. We use the two-input PID controller in the return air fan volume matching. Thus, the return fan speed is modulated to maintain a set difference between the amount of air supplied and returned from the occupied space. Another key benefit is that the programmable minimum speed of the VLT/HVAC drive is used to ensure that the ventilation requirements are met as the building load changes. Above the minimum speed, airflow is varied based on temperature, carbon dioxide, or other variables. With this, we have come to the end of this module.